Good morning, everybody. Hope you all are having yourselves a wonderful Tuesday morning. Today we're going to continue talking about what we started yesterday, or at least we're going to continue our lesson from yesterday. But instead of talking about independence, we're going to talk about dependent probability. It's really what the message of the whole week is going to be: independent and dependent probabilities. Now, unlike the independent probability where you just multiply the individual parts together and your denominators don't change, dependent probability has it where if you want to find the probability of two events occurring simultaneously, or their intersection, you multiply the probability of the first one times the probability of the second one, given the fact that the first one has already happened. This is not B divided by A. This is saying that A has occurred. Now, you're going to calculate the probability of B, but the numbers will be different now. So let's see an example of this. A bag contains 5 quarters and 4 pennies. We want to find the probability of drawing a quarter and a penny without replacing them. So meaning when I take the first coin out, my number of coins left in the bag are different. And so if I want to write the proper terminology for this, the probability of drawing a quarter, or the probability of a quarter and a penny, which I'm going to use as a cent symbol, is going to be equal to the probability of finding a quarter times the probability of finding a penny, given the fact that a quarter has already been drawn. So we know that for any probability, it is going to be E over T, meaning the amount of things that I want to have versus the total amount of things that there are. So the probability of finding a quarter would have to be 5, because that's how many quarters we have, and out of 9, because there's 9 coins in total. Now for the second one, we multiply. And how many pennies do we have? 4. And except we've already taken a quarter out, so we're no longer going to have 9 coins. We only have 8 coins. Now if you want to simplify this 4/8 into 1/2, that's totally fine. You don't have to. You'll always be able to simplify at the end. If you multiply these directly, because that's how you multiply fractions, you multiply directly. 5 times 4 is 20. And 9 times 8 is 72. Now, since I know that both these are even, I'll be able to divide them by 2, but since I could simplify that, I could probably simplify this even further. 20 over 72 is the same thing, if I divide by 4 on both sides, top and bottom, is 5 over 18. Just looking at my notes over here. Now, ladies and gentlemen, this 5 over 18 is our probability. That means that if I wanted to get a quarter than a penny, it's 5/18. But also you can interpret it as, if I ran this experiment of drawing 2 coins, out of 18 times that I would run this experiment, I'd most likely get a quarter and then a penny out of 5 of them. So you can kind of see it as a lot of trial and error. That's one way to interpret probability. Now, is this guaranteed that if you do it 18 times it's going to happen 5? No. But that's just how likely it's going to happen. Let's move on to something a little bit different, a reflection. Suppose a wallet contains 5 $1 bills and 3 $5 bills. If a person reaches in and pulls out 2 bills, the probability that the second bill is a 5 is 21 out of 56, or 0.3750. Our reflection is, why is the above situation a conditional or a dependent probability? Just take 5 seconds or how long it takes for me to draw these bills out. It's not good bills, but Now, ladies and gentlemen, if I have 5 $1, this being my $1, and 3 $5, I almost said 3 $3, and that would have been hilarious. I want to get my second bill to be a 5, but I have to draw 2 bills, which means if I draw one of these, well, if I draw one of those, that bill is no longer able to be drawn, which means instead of having 8, I now have 7 bills to choose from. So where we start off from 8 bills, we then go to 7 when we draw. Same thing happens if whether or not you draw 1 or 5 first. You could go from 3 $5 bills to 2 if you drew at 5 first, or you could go from $1 bills to $5 bills. So all our numbers are constantly changing depending on what we're drawing. So that's why this is a dependent probability. Now I want to go back to black ink, make it more official. Now, this is going to be an example on a conditional probability, and one that we have to be super careful about in how we read it. A bag contains 4 blue marbles, 3 red ones, 6 yellow ones, and 2 green ones, and 1 purple marble. This bag contains a lot of marbles. In fact, let's make sure we get a good total on that right now. That should be 16 marbles. What's the probability that you draw 5 marbles and get 1 of each color? Now the big question is this an independent probability? Is this a dependent probability? Well, it's definitely a dependent probability because when it says that you draw 5 marbles, it doesn't say that I'm putting the marbles back, so you can only assume that I'm keeping the marbles. So, if I want to draw this out, to make it easier on me, I want to put this in categories, where I only have a specific amount of each thing that I want to get. And I'm going to put this as the probability of all colors if you ask my students, I always like to write out my equations, is the probability of a blue. Now we did say that the probability is going to change for each new thing. So times the probability of a red, given the fact that blue happens, times the probability of a yellow, given the fact that a red occurred, times the probability of a green, given the fact that a yellow occurred, times the probability of a purple, given the fact that a green occurred. Now, ladies and gentlemen, this might look like a whole bunch of just gunk and a whole bunch of letters and probabilities, but it's actually pretty simple once you start breaking these things down. How many marbles do we have in total? 16. How many purple marbles are there? 4. Now, let's consider the reds. Has our number of reds changed? No, so that's still going to be 3 on top. But the total number of marbles did change. Instead of 16, now there's 15. How many yellows are there? 6. How many marbles do we have now? 14. How many green ones are there? 2 out of 13. And you can probably see where I'm going with this. How many purples are there? 1 out of 12. Now, ladies and gentlemen, if you multiply all these together, you would get a really big number. If I wrote this down correctly, that is 144, which it's 12 times 12, because 4 times 3 is 12, 6 times 2 is 12, and 12 times 12 is 144. 144 times 1 is 144. So that's 144 out of 15 times 16 times 15 times 14 times 13 times 12. Or it's close to a factorial. That's 524,160. So 524,160. Meaning if you did this experiment 524,160 times, you'd get it in this order or with this set, this combination, about 144 times. Now, let's simplify that, because this can definitely be rounded down. Apparently, this can be divided by 144, and that's 1 out of 3,640. 640, which is pretty awesome. Oh, so one thing I do want to talk about before we go on is that if you did this experiment 3,640 times, it occurred once. So this is an incredibly, incredibly low probability. It is very unlikely that you would get 1 out of each color. But one thing we should definitely notice is how each one of these denominators changed when we tried to get a new color. None of them were ever the same. Alright, let's wrap this up. If you have 8 blue Powerades and 6 red Powerades and a cooler and you grab 2, what's the probability that you grabbed a Powerade of both colors? Meaning that you can only get 1 blue and 1 red. Now, personally, I prefer a fruit punch Powerade. That's just me. So the probability of a blue and a red is going to be equal to... Now, one question that we have is, does it depend on what order that you go? Could you start with a blue and start with a red and get the same values? Well, let's figure that out. I say yes. For this one, it does not matter whether you start with blue or you start with red. Because, that's not meant to be a multiplication sign, it's meant to be an equal sign. That's the same thing as the probability of red times the probability of blue, given the fact that red exists. How many blue Powerades are there? 8. How many are there in total? 14. Well, it means you now have 6 red Powerades, 13. Well, let's reverse those numbers. Let's reverse those numbers and we see what we get. Well, how many red Powerades are there? 6. Total 14 times 8 out of 13. Well, the thing is, 8 times 6 is the same thing as 6 times 8. And this has not changed. It's still 13 times 14. Hello, Minerva girl, how are you doing? I guess my cat wants attention. I'll give her attention in just a moment when I finish this lesson. 8 times 6 is 42, if I am correct. No, it's 48, because 6 times 7 is 42. So it's 48 out of 182. For a second, I thought I did the math wrong. I was like, oh no. So yes, it does not matter whether you do red Powerades first or blue Powerades first, because multiplication is commutative. It changes, you can flip it back and forth, but it doesn't change the operations. And this simplifies down to 24 out of 91. Now, I don't believe you can simplify this down any further because 91 is a prime, I'm pretty sure. And so you could do this experiment 91 times and only get 1 Powerade of each color 24 times, which isn't bad. It's about a third if I'm looking at it correctly, almost a third. But I think that's where we're going to leave off today, ladies and gentlemen. Hope you all have yourself a great Tuesday. I look forward to seeing you again next year. I mean, this isn't the end of the episodes, but I want to see you guys in person and teach in person next year. Bye.